Why is that important for us? Why we are wasting our time studying this, right? Because eventually you can think about the start of the time, P0, to be your data distribution. Okay? Now, you can start from data distribution, and then you can move forward in time till you end up with the latent representation, meaning that pure noise, right? Can we do this? Can we start from data and convert it into pure noise? We can do it. We have seen it before. We're going to see it today, right? But intuitively, just add noise, right? Add Gaussian noise to your data and reduce the power of data. Reduce power of data, increase power of noise. Reduce power of data, increase power of noise. This is going to go forward till at some particular time you are pretty much left by noise, right? So you move forward in time till you get to noise. Know how to do it, which sounds feasible, then you can eventually move backward, right? Just use the Anderson equation, right? Now, start from your image, just make it noise, and then see what you did when you were going forward to get to the noise, right? Give those things to Anderson equation, then you're going to get backward to your data from noise, right? This is exactly what we want to do. We want to get from noise to data, right? Everybody's clear what we're doing? So this is the idea of diffusion in diffusion process. So if we can move forward in time such that we start from one data sample, one image, and end up with noise, pure noise, then we can move backward from noise to the data using the backward diffusion process. Okay? Now, how we can start from data and end up noise? Look at this particular equation. Okay? Don't think about what it is in terms of diffusion. Just look at it right now. I start from one point x0, so it could be my data, right? I start from something x0, and then I process it like this. So each time I am computing x that I have minus some beta. This beta is something that I just designed. Beta x delta t. Delta t is a very tiny number, right? Plus this term, which is eventually again given in terms of beta and delta t, so I compute it, times the square root of delta t epsilon I, right? So what I'm doing, I'm getting x, I'm doing some calculation on x, then I'm adding some noise, right? That's the whole thing that I'm doing, right? But this guy, when you look at it, do you think this is a diffusion equation or not? This is indeed a diffusion model equation, a diffusion dynamic. Why? Because if I just treat this guy to be f, the drift term, and this guy to be g, the diffusion coefficient, so I replace this square root with g, and this beta x by f, then this term is eventually going to be to fit exactly to the equation, the diffusion equation that we had. Okay? So this equation is a diffusion equation, meaning that I have corresponding to this equation one other equation which is the reverse diffusion, right? Which explains how I can move backward in time. Keep that in mind, okay? Now, for the moment, let's see if we can simplify this equation a bit more. So one thing that I can do here is that I can look at this square root of delta. I can take this square root inside, right? Then I'm going to remain with beta delta. Here again, beta delta. And here also I have beta delta, right? Correct? Now, you can go ahead at home and do a bit of calculation. It's not a very hard calculation. At the end of the day, you can see if you define this 1 minus beta delta to be alpha, okay, then you're going to end up, that equation above is exactly this equation, okay? So this is going to be, look at this equation here, 1 minus beta delta x. I'm going to write it down alpha x, right? And then this term, all of that term is going to simplify to 1 minus alpha squared, okay? So alpha times my x plus 1 minus alpha times random Gaussian noise, right? Everybody's cool? Okay, so now, from now on, I'm showing this 1 minus alpha to be alpha bar. What is the property of alpha bar and alpha together? Exactly, 1, exactly. So if you think about alpha and alpha bar here, so alpha squared, so any alpha I squared plus alpha bar I squared is going to be 1, right? Because alpha bar is 1 minus alpha squared, right? So if you square it and then you sum it up, it's 1, right? Everybody's clear, right? Okay, so let me clear up things for you again. So this is the equation that we have. So that diffusion process that I showed you is going to end up being something like this, right? So every single time you start with some x, every single time you multiply this x by some alpha, right? And then you are going to add it with some Gaussian noise, and that Gaussian noise has variance alpha bar, right? Everybody's cool? Now, one question. How is alpha? What is alpha? What is the range of alpha? Look at this equation and tell me. What is a feasible? 0 to 1, that's right. Another thing, is it close to 1 or is it close to 0? That delta t, what is delta t? A very tiny move in time, right? So delta t should be very, very, very small, right? So this means that 1 minus beta delta, doesn't matter what beta is. That guy is very close to 1, right? So alpha is very close to 1. Alpha bar is very close to 0, right? So you have your data, x. Every time you're just scaling it down a tiny bit, right? You just make it a tiny bit smaller than 1, right? And then you add that amount of power you lost, Gaussian error, right? Now, you keep on going like this in time. What's going to happen if you do it for a very, very, very long time? End up with only noise. Exactly. So this is what we call, I think we had this example when we talked about Markov chain in the sampling part in energy-based models. This is what we call it Ornstein-Uhlenbeck process. So this is a random process. You can prove that this random process at time moves forward, at time goes to infinity. The final distribution, the distribution at time, at this time, the distribution at this time is going to be pretty Gaussian. Gaussian zero mean unit variance. Okay? The only thing that you need to make sure is that you start with something zero mean and unit variance, which is not a hard thing. So if I have any x, if I start with any x, I just subtract it from its mean. I normalize it with this variance, so it's going to be zero mean unit variance something, right, coming from any distribution. And I put it inside this equation. This goes up till it's going to end up with one Gaussian process. So every single time that I move forward, because of this property alpha squared plus alpha bar squared equal by 1, I'm going to keep the power to be 1, so my variance is not going to explode, right? But the feature is that when I press it enough in time, then I'm going to end up with one Gaussian process, right? So what is this equation doing for us? This is starting from one sample, right? One sample, which could be our data sample. And it's going forward till it takes us to noise, right? Pure noise. Now, if I can go forward in time and end up with pure noise, now, since I know what is the process which is taking me to that direction, I can write down the backward process, right? Using the Anderson equation, right? And then I get one equation which explains starting from a Gaussian noise, moving backwards step by step to get to your data distribution, right? Everybody's clear? You get the idea? So this is what we call it the noising process. The noising process is the forward diffusion process which turns a data sample into Gaussian noise. Okay? The The forward process, we could explain it. It's going to diffuse one sample that we have into one pure Gaussian noise, right? Now the point is that once we have this forward process, now we can just build a reverse diffusion using the Anderson equation, right? So what Anderson told us in his equation is that since you know the forward diffusion that is taking you from data to noise, now I can give you a backward diffusion, which is going to, if you sample from the same noise, which is a Gaussian noise, and put it inside this equation, then this is going to gradually take you back to the data, right? The distribution that you started with, right? So this is the idea, and let's just look at the equation once again. So this was the forward equation, right? So I know that I represent everything in form of alpha and one alpha bar, but the original equation was this one, which was fitting exactly to the definition of a SDE, right? Now that you have this kind of a forward process, then you can go ahead and do a bit of calculation, but that is going to, you don't really need to focus too much on the details. Just take, for example, this beta is going forward, right? When you are at particular time I, the last time, the capital I, then the point that you're going to start with is beta I minus I, right? So the last one is beta I, then the previous one is beta I minus 1, and so on till forward. Same thing happens here in G. So for G, it's quite simple. You just take that expression, whatever you have there, and then you just replace I with I minus I, right? You just reverse the time, right? So you started with G0, G1, G2, you end at Gi. Now you're going to again make it Gi, Gi minus 1, Gi minus 2, till you get again to G0, right? So that one is easy. For F, the first term is exactly, the first term here is exactly F reversed in time, right? So it's going to be F of I minus 1, I minus small I, and then X backward, right? Where X backward is going to look like your forward process at time I minus I, right? So that's it. This is the G term that we had. So G squared, I'm going to replace it here. And this is the term that I need in the Anderson equation, right? So what is this term? This is the gradient of log probability of I minus I, right? Meaning that inside this equation, when I want to start from here and move backward, I need to know F, which I do know it, right? I need to know G, which I do know it. In addition to that, I need to know something else. And that thing is that the gradient of the logarithm of probability at this particular time, right? So what is this gradient of log probability? What did we call it? Score, right? So I need to know the score function at this point, a score value at this point, right? In addition to my forward things, I need to know a score to be able to move backward to here, right? Again, when I get here, I need to know a score at this time to move backward here, and so on. Everybody's clear? So things from the forward are all okay. This red guy is a bit of problem because this needs us to know a score, right? But let's go forward and see what we can do about it. So if we want to get back from latent, the Gaussian, to the data, what we can do, we can just sample one Gaussian noise, right? We are here at the end of the time, right? And now we want to move backward. Now that we want to move backward, every time we just move backward with this, backward process. So from this point, we go 1 point backward, 1 point backward, and so on, till we get here. If we keep on going I number of times, then the last thing that we're going to have here is going to be a data sample, right? Now, one question. Is this data sample exactly the data sample I started with? No, this is a new data sample, right? No equality, but it's coming from the same distribution. So if I started from a cat image, I'm going to end up with a cat image, right? But this is not going to be the same cat, right? It's not exactly same sample, right? It's a sample from same distribution, right? Okay, so I can do this. That's cool. This is the whole idea of diffusion. But the question here is that what do we have in this backward equation what we don't have, right? So we know what we have. We eventually have those f value and g values. I mean, the expression inside, which are coming from the forward one. But we have a bit of problem with this score function, right? So I start with data. I go forward. In this forward, I have everything, right? For forward, I don't need to do any learning, right? When I'm moving forward, I don't need to do any learning right now, okay? So I'm moving forward. Then I start with data. I have a data sample. Then I add noise. I can do it. Again, add noise. I can do it. End up noise. I can do it. So everything is fine. And then since I can do this, I mean, since I have data sample and I do know this process, I can generate that Gaussian process, right? But the point is that when I want to move backward, I start sampling this guy. Sure, I can sample one Gaussian noise, but then I need to go over this process, right? And if I want to go over this process, in addition to all things here above that I do have, I need to have score, right? I need to know the score value. Now, the important thing that you should pay attention here is that which score value you need to know. Which score values you need to know? The one you sample from, roughly, yes. Yeah? Now, I want to know a score, right? How can I learn a score? I mean, definitely I don't have a score. I need to learn it, right? If I want to learn it, what should I do? Again, get back to high-Ferdinand result, right? So you might say that, okay, you're back to square one. So you did all of this process forward in time, backward in time, but you ended up needing a score. And we don't have a score. We say it's very complex to compute. But there is one tiny trick here, one tiny twist here. The point is that we don't need to know the score function of the data distribution. This is the whole trick. Okay? Let's look at it together. When I want to just move backward in time from noise to the data, what do I need? I mean, first of all, look at this expression here. I start with this guy, right? When I want to compute the backward trajectory to the next point, I need to know the score function at this point, right? And the score function of this guy is given by normal distribution, right? I can easily compute it, right? That's not a big deal. I do know what is the normal distribution. I can compute the gradient of log. So I do have the score value. I put this value, x0, at that score function. I get it, right? That's no problem. This is going one step, right? Backward in time. Now I get here. What do I need to know? The score function of this guy, right? This pi minus 1, the score corresponding to pi minus 1. Is it the data distribution? No, it's the noisy version of data, right? Now again, I'll go backward. I need to know a score for pi minus 2, right? And I keep on going till I get here, I minus 1, right? At this point, what do I need to know? Pi minus 1, right? I need to know the score function of P1. I need to know the score function of P1, right? Then, when I know the score function of P1, I can again compute the backward trajectory, and I get my data sample. Do I need to know the score function of P data? Not anymore. No? Right? So I don't need to know the score function of P data. You look at this expression here. This green one is easy to compute. These red ones, none of them is the score function of data. But high-Ferdinand result was to estimate the score function of the data, right? That was different. Everybody's clear? So every time you're moving backward in time, you eventually are just computing the score function of the noisy version of data, not the data itself, right? So, for example, at particular time 1, if you want to know the score function P1, you eventually want to know the score function of this random variable, x1, which is your data sample plus some noise, right? If you want to know the score function of P2, you eventually want to know the score function of this x2, which is x1 plus some noise, right? And again, x1 itself was x plus another noise, right? And if you just sort things out together, at the end of the day, you have one term which is only your data, one term which is only your noise, right? Everybody's clear? So all the time, every single of those red terms that you see above, all of those scores are scores of a noisy version of data, not data itself.